In this video, I'm not actually going to define any functions for you, but we are going to discuss, given the graph of a function, how to come up with the graph of the derivative of a function. Now, big important things to look for are going to be where the slope of a tangent line would be equal to 0, or where it would be undefined. Now, typically, for those kinds of points, we would be looking for something where the slope of a tangent line would be 0. And using the parlance of pre-calculus, those tend to happen where you have a local maximum or a local minimum. So if I were to attempt to draw the derivative on the same set of axes, then right here, this x value right here, we'll put that right about here. And then this x value right here, we'll put that over here, about the same distance away. The value of the slope of the tangent line at those 2 points would be equal to 0. So for the graph of y equals f of x, on the graph of y equals f prime of x, we would see that those 2 points would have a value of 0 corresponding to the slope of 0 that you see here. Now to the left of the left point, if I were to draw in any tangent line, I would see that that tangent line would have a negative slope due to the fact that the function is decreasing at this point. So decreasing here corresponds to negative over here. In between our local maximum and in between our local minimum and our local maximum, if I were to draw in any tangent line, I would see that it would have a positive slope due to the fact that the function is increasing. So between these 2 points, we are going to see positive values. We don't necessarily know how positive, just that they're positive. Beyond the local maximum, the function is once again decreasing. Decreasing implies that slopes of tangent lines are going to be negative and getting larger in the negative direction. So, when the original function is decreasing, the graph of the derivative will be negative. If the original function is increasing, we'll see positive, and once again decreasing, we'll see negative. Now, in the event that your graph has some sharp corners on it, that means chances are pretty good that this thing is defined piecewise with those nice sharp corners there. In fact, this is comprised of straight lines, so any tangent line would have the same slope as whatever we see here. So this point right here, we're going to label as this right here, and then this right here, we'll label as about right here. So in between these 2 points, I see that the slope is negative and constant. So what I'm going to do is draw something that is negative and constant. To the left of the left point, I see something that is constant and positive as far as slope is concerned. So constant and positive will look like the following: constant and positive. And over on the right-hand side, once again, slope is constant and positive, so we're going to draw that in like so. Now, these places where the function is continuous, but the derivative doesn't necessarily exist at those points, we're going to talk about those later on in the chapter. They do have a special name. So these would be considered jump discontinuities in the first derivative. Finally, we have this nice curvy-looking function right here. I see that there are 3 points where we're going to see a slope of a tangent line being equal to 0. One right about here, one right at the origin, and then another one right here. We'll go ahead and label those points right here, and right here. The slope of the tangent line is going to be 0 at all 3 of those points, so I'm going to label those as 0 here. Now we can do something similar to what we did with our first graph and identify, are we decreasing or increasing on each of these intervals? So I see increasing followed by decreasing, followed by increasing, followed by decreasing. So for the derivative, we are going to see a positive, negative, in terms of the slopes. So in between these, we'll see negative. In between these two, we will see positive. Beyond here, we'll see positive, and beyond here, we'll see negative. Additionally, something should be pointed out. Here we see a function with 2 turning points, 3 x-intercepts. These things imply that this is probably a cubic polynomial. We know from some other problems that if you differentiate a cubic polynomial, you get a quadratic polynomial. So it's no surprise that the graph that we came up with here is a parabola. Similarly, if we were to look at this graph down here, I see 1, 2, 3 turning points. I see 3 x-intercepts, but that one would have a multiplicity of 2. That implies that this is a 4th degree polynomial. Once again, if you differentiate a 4th degree polynomial, I would anticipate that we would wind up with a 3rd degree polynomial, which makes me feel pretty comfortable with our final answers.